compound events just means two events are happening at one time. So it's said that if one outcome of an event does not affect the other outcome of the second event, then they are independent events. But when the outcome of one event does affect the outcome of the second event, then they are dependent events. If these two events can't happen at the same time, we then call them mutually exclusive. So if we're trying to find the probability of event A or event B, so that's what this is saying right here. We need to find the probability of each of them and then subtract the overlap or the event that they are when they are both things. And that'll make more sense once we start looking at some examples. So to find A or B, we find the probability of A, the probability of B, subtract the overlap or subtract the time when A and B occur at the same time. So when you're finding the probability of two independent events, all you do is multiply the probabilities of the first event times the probability of the second event. So A and B, you just multiply together. To find the probability of two dependent events, multiply the probability of A and the probability of B after A occurs. Again, it'll make more sense with some examples. And then finding the probability of one or the other of two mutually exclusive events, you add the probabilities of the event of the probability of the second event. Probability of the first plus probability of the second. That's for your or. So it says as part of a board game, you need to spin the spinner at the right, which is divided into equal parts. Find the probability that you get a 25 on your first spin and a 50 on your second spin. So spinning the spinner, they're mutually exclusive. Whenever you spin on the first one, that's not going to affect what you spin on the second one. So the probability of spinning a 25 and then a 50, there's two 25s and one 50. And there's 8 sections. So, and 2 8s times 1 8 gives you 2 64ths. You could do it as 1 over 32, and it's about 3.1%. So number 2 says a bowl contains 36 green grapes and 14 purple grapes. You randomly choose a grape, eat it, and randomly choose another grape. Find the probability that both events A and B will occur. So we want the probability that the first one is green and the second is green. So green, then green again. So we want green and green. So we are going to be multiplying them, but what's going to happen is the first event where the first grape is green, there's a total of 36 green, and there's a total of 36 plus 14, so 50 total grapes in the bowl. So 36 out of 50. But once you've now eaten that first grape, there's no longer 50 grapes in the bowl, there's only 49. And there's no longer 36 green grapes because you just ate one of them. So now the probability of the second event is only 35 out of 49, which gives you 1260 over 2440, or 2450, I'm sorry, which is about 51.4%. So those would not be mutually exclusive events because what happens with event B is affected by what happens in event A. And then your last one, it says a card is randomly selected from a standard deck. What is the probability that the card is a heart or a face? So probability of a heart or face. So the probability of a heart, there's 13 hearts in a deck. Plus the probability of the face cards, there's 12 of those. Again, if you guys want a laminated picture of deck of cards, I have them. But if we want one or the other, we don't want the ones that are a heart and a face card. So we need to subtract any that overlap. And are there any cards that are hearts and face cards? Yes. The King of Hearts, Queen of Hearts, and Jack of Hearts. All face cards, all hearts. So those are both of them, and we only want one or the other. So we end up with 22 out of 52. So about 42.3%. So those are your three combinations. So mutually exclusive, just one and the other, multiply them together. One and the other, but they're not mutually exclusive, so we have to multiply by the event B after event A has occurred, and your third one or the other, where you have to subtract the overlap or the part where they are both events. Number 4 talks about a survey of pet owners, and it says of 200 pet owners, 103 owned dogs, 88 owned cats, 25 owned birds, and 18 owned reptiles. So letter A says that if none of the respondents owned both a cat and a bird, so there was no overlap, that people owned both of them, what is the probability that they owned a cat or a bird? So the probability of cat or bird, if there's no overlap, there's nothing to subtract. So it's just the probability of the cats, which is 88, plus the probability of bird owners, which is 25. So you have a total of 113 out of 200. So about 56.5% of the owners, or chance of the owners being a cat or bird owner. So letter B says, okay, well, of the respondents, 52 owned a cat and a dog. So that's the overlap. 52 owned both. What is the probability that the respondent owned a cat or a dog? So here, if we're trying to find the probability of cat or dog, this is where we do add up both parts, but because there's overlap where people own both, we need to subtract that because we want cat or dog owners. We don't want to include cat and dog owners. So there's 103 dog owners plus 88 cat owners minus the 52 that are owners of both. We want one or the other. So 103 plus 88 minus 52 gives us 139 out of 200. So about 69.5%. And then the last one says, okay, well, of the respondents, 119 did own a dog or a reptile. It's telling us that's who owned a dog or a reptile. So what is the probability that they owned a dog and a reptile? So what we're finding here is the overlap. So we want to know if the probability of a dog or reptile is equal to 119. We're trying to find the overlap part to subtract. So we're going to add dog owners, 103, plus reptile owners, 18. And subtract what we're trying to find, which would be both of them, the ones that own a dog and a reptile. So 103 plus 18 is 121, which means that 2 owned both. We would just solve it. So probability of this or that is the sum of both of those events, subtracting the overlap or the part where they are both.